should I just share my screen now?
Let's see. Yes, please. Yep.
Perfect. Can you see that?
Yeah, we can see you.
Amazing. Okay. So thank you firstly for the kind invitation to talk today. So as you've mentioned, I'm going to talk about incidents that we face while undertaking ECMO, discuss how to deal with these incidents, and how we can put systems in place to prevent such incidents happening. And should they happen, how we should try and minimize the impact on our patients. So just a few, I suppose, dictionary definitions. So when I was asked to put the presentation together, I thought, well, what is classed as an incident or an adverse event? So the dictionary states it's an undesirable experience associated with a medicinal product, which in this case, it is the ECMO circuit. Risk is the degree or the possibility of this thing happening. And then finally, moving on to safety. So this is defined as the protection against the risk or the injury or the danger. So when we put steps in place to reduce risk happening, this is what we're talking about with regards to the safety of our ECMO and our ECMO care. But before I go into this bit, I think it's fair that we only discuss what adverse events or what incidents we see whilst undertaking ECMO. So there is plenty of literature out there about adverse events and complications. If you look in the big ELSO Red Book, the main complications that are commonly written about are membrane lung dysfunction, air in the circuit, circuit disruption, console or power failure, inadvertent decannulation, and gas supply interruption. And basically, as ECMO practitioners, we're expected to be able to identify and deal with these scenarios proficiently. So the incidence of these events. So there, like I said, there are lots of data out there, but this paper from Brody et al., a little bit old, shows us that the #1 circuit-related incidents, which is probably no surprise, is circuit component clots. Now, normally this probably isn't a massive incident. It's just an irritation because our hemofilter might fail, or we can't give drugs down a stopcock, or we lose our pressure monitoring. However, if we move on and we look at the biggest, the second largest circuit-related complication, it states oxygenator failure at 5.9%. It goes on to say circuit change at 2.4%, but it doesn't identify why we're doing that circuit change. Is it because the circuit is failed or because of a clinical incident? Or is it just because we have a patient that is bleeding? So it's a bit hard to ascertain where we're going with that one. And then when I teach on ECMO courses, I always ask people that come to learn about ECMO, what is your biggest fear about looking after an ECMO circuit? And everybody always says it's air in the circuit or pump failure. And actually, the risk of that happening is very, very low, 1 and 1.2%. But the problem is because it can be so catastrophic and we need to respond so quickly, it is the thing that people fear the most. So what I'm going to do now is talk through the different clinical incidences stipulated by ECMO and go through them, and then we'll talk about safety a little bit more at the end. So if we look at membrane lung dysfunction, it basically is caused by 3 different etiologies. So we have the hematological etiology. So as we know, ECMO is a non-biological surface with a high surface area, and it activates an inflammatory and coagulation pathways leading to systemic coagulopathy, fibrin, and clot deposit. And this in turn causes the membrane lung to start to fail. Or the other thing it can cause is hemolysis, which, as we know, and again, if you look in the Red Book, hemolysis is the destruction of red blood cells, which is very bad for the patient's prognosis, particularly with regard to kidney damage. So we need to be aware of this. The second way a membrane lung begins to fail is the obstruction of the gas exchanging fibers, so the polymethyl pentane fibers. As clots deposit within the fibers, it reduces the surface, the amount of blood flow through those fibers, therefore reducing the efficiency. And eventually, it will become a point where the ECMO lung isn't providing enough flow for us to oxygenate our patient. And then finally, we get impaired gas exchange, either by water within the fibres or condensation, or debris clot from the outside of the fibres. So essentially, that increases the distance our gases must transfer across, slowing and reducing the efficiency of our membrane lung, and therefore eventually the membrane lung fails. So if we look at this really nice algorithm by Zachariah et al., it actually identifies the things we need to look for in those 3 criteria, so we can identify the membrane lung. So we talk about clinical incidences, we know what it might happen, we need to know how to identify it. So we need to be looking at our coagulation labs, whether it's INR, APTT, and many places commonly look and test for hemolysis on shift to help us identify that our membrane lung might begin to fail. Then we need to look at our pressure monitoring. So we measure our pressures pre-oxy and post-oxygenator on membrane lung, and that will tell us how much resistance there is to blood flow in the circuit. So that's another important thing we need to be aware of. And then finally, we can actually calculate the efficiency of our membrane lung. And the beauty of this algorithm, it actually gives us some numbers to go as a guideline. So if you don't do a lot of ECMO, it's a great little reference. But the long and short of it is, as an ECMO practitioner, if a membrane lung is starting to fail, we need to look at the colour difference in our tubing, the rise in pressure, our mean pressure gradients, the decline in post-oxy gases, and finally the decline in obviously the patient oxygenation marking. So what's our patient saturation doing? And these will all give us a sign as to whether our membrane lung is failing and indicate whether we need to do something about it. So how do we deal with it? Well, the membrane lung, we need to, one, assess how quickly it is failing, and we need to assess where we're at with the patient. So the patient may be close to coming off ECMO. You might need another 12 hours potentially. So you might want to try and continue and persist by increasing the flows or increasing the FiO2 on your oxygenator to try and limp it along, because as we know, every circuit intervention puts the patient back. The other option is we change the membrane lung, or depending on your hardware or your clinician's preference, it's a circuit change. In my organisation, we change the membrane lung, but we have the ability to do that. So in doing that, we have to obviously have a protocol of how to do that, because that makes it safe practice. So we optimise the ventilation of our patient, we clamp the patient off from the ECMO circuit, and we cut in the drainage line and the returnage line near the cannula if you're doing a whole circuit change, and just the oxygenator if you're doing a membrane lung change, obviously making air-free connections. So now moving on to one of the second sort of clinical incidences our ECMO didactic tells us we should be aware of. So it's gas line interruption. Now, normally, gas supply interruption is not membrane lung failure. It's because what you see is a sudden loss of oxygenation. And the first 2 things you will notice is a loss of saturations of patients and lack of colour difference between the drainage line of the ECMO circuit and the return line of the circuit. Now, it's like I said, it's very unlikely to be membrane lung if it happens so rapidly. Now, in this situation, obviously, you will see the alarm start to go off, your lines are very dark, and you want to start providing some ventilation and support. And if it takes some time to fault find or whatever, you may need to do CPR. But normally, this process commonly happens when you've moved the patient, whether it's from another bed space or to CT or whatever. So you've been on an oxygen cylinder and it's been failed to be reattached to the wall gas cylinders, or the oxygen cylinder has run out. Other incidences where we've moved the patient, that the gas line tubing comes disconnected. So in this scenario, one of the most common ways to avoid this sort of incident is to use checklists. So moving on to the third major incident that we may see in our ECMO patients is pump failure. Now, as we know from the earlier slide, we only see this in about 1% of our sort of ECMO incidences. And this can be caused by a number of reasons. So it can be caused by pump thrombosis in the pump head that completely stops it working. If you're using a centrifugal pump, it can be caused by air that's completely occluded the inlet of your pump, so you cannot push any forward fluid. We can all, in that situation, there is nothing really you can do apart from change that component. So you have to momentarily come off ECMO and change the component. Other than that, we have a console or pump failure. Now, this can be just the mechanics of the pump failure, or it can be the internal batteries dying. And I once had an incident where the batteries were affected by extreme weather conditions and the console just died. So it's a very scary process, and how you manage it depends on the hardware you've got. So we'll talk about that on the next slide. And then the third thing that might cause a pump failure is, the motor head failing, or if you're still using roller pumps, which is still perfectly acceptable to do, even though most of us use centrifugal pumps in modern age ECMO, obviously rupture of the raceway. And all these have slightly different ways of dealing with them, but having good protocols to do it is is absolutely essential. So normally, if your pump began to fail, you'd momentarily clamp off your patient, prevent retrograde flow, and re-establish some form of RPM. So many systems come with hand cranks, so that's great. But if you have a system that doesn't have hand cranking to re-establish those flows, then you have to literally swap the console. So in the case of if anybody that has a CentriMag system at the top, you always have to have 2 consoles available. So then we come to the other rare event, but the one that causes the most fear in ECMO practitioners. So I call it the jaws of the ECMO world. So if air manifests itself in a circuit, the first thing to do is obviously isolate it from the patient, and then you have to identify the source of air. So the source of air can be errors in priming, errors in turning stopcocks the wrong way, particularly if you've got negative access on the negative pressure. It can be a CV catheter placement that's managed to entrain air into your circuit, or by exposing the drainage holes of the cannula. So when you do identify air, you need to make a choice whether you're going to de-air the circuit or whether you're going to change the circuit. And I would say that you have a choice, because if you have big chunks of air, it's great. It's pretty straightforward to remove. However, if you have a lot of frothy air within your ECMO circuit, it's very difficult to remove, and a circuit change may be beneficial in this situation. So there I've briefly talked about how to de-air and how to change the circuit. So changing the circuit is a simple clamp off, cut, and re-clamp the new circuit. Obviously with de-airing, it's slightly different. We need to find a way to move the air to the nearest access point. So I always think about evacuating an airplane. If for an emergency thing, you move the air to the nearest exit. But you have to remember that air removal is a displacement reaction. We need to have fluid in to displace the air which is pushed out of the circuit. And the most common failure when anybody's doing any de-airing, particularly if they're not perfusionists, is they forget to hang a bag of fluid and open that bag of fluid to displace the air. So on to, we're nearly there with regard to the ECMO, the ELSO incident criteria. So then we have accidental decannulation. So generally we will have a 2 cannula, a drainage cannula, and a return cannula. So the drainage cannula, it's important to remember, if that becomes displaced, it is negative pressure, it's suction, so it will entrain air very quickly into your circuit, so it can be very catastrophic very quickly. Whereas the return cannula, if that becomes dislodged and displaced, obviously we have a risk of exsanguinating the patient, because it literally expels all the blood from the reservoir. Which essentially the reservoir is the patient in this, so it expels all the blood from the circuit. Now, I think from my personal perspective, I think I prefer to deal with the positive pressure or the return cannula, because it's very easy to adapt a bleeding protocol. There's blood on hand, lots of fluid, so it's much easier to resuscitate that circuit. But in those situations, again, you must have a clear protocol of how to deal with it. So clamp off your circuit, call for help. If the cannula has completely come out, you must compress the site, and you must support the patient while you're trying to determine whether you're going to recannulate or push the cannula back in and deal with the circuit, whether you need to de-air that. So I think this is the final ECMO incident that's noted in the ELSO book. So we have circuit disruption. So this is very similar to decannulation, but basically it's in a different part of the circuit. So circuit disruption is anything that stops the pump from working, essentially. So air entrainment by perhaps a stopcock being turned the wrong way on the negative pressure side, fills your head with air, and you cannot obviously push fluid forward. Or the opposite, you see a lovely picture on the right hand side where a stopcock fell off, it got caught and sheared off, and it sprayed blood all over the ambience. Now that looked like a lot of blood in the corner there, but actually in actual fact the patient didn't require any transfusion despite having a reasonable amount of blood loss. Not that it was ideal, but we managed to deal with it rapidly because we knew what to do. We had access to an extra component. We compressed the site, or we put our finger over the hole. We managed to support the patient while we're off ECMO to very quickly change the component. So again, these things happen, we know, but you need to have good protocols and procedures in place to rectify the situation. So although, go back a slide one moment. So although I've mentioned, all circuitry issues, we've also got to remember there are adverse events during cannulation that we need to be aware of and be prepared for. So when cannulating, you can have cannula damage, clamping the wire wound cannula at the wrong site may cause problems, particularly down on the drainage side. We can have cardiac arrests. So if you're going for a VV approach, you may then have to change your configuration following cannulation to VA if the patient's arrested. And also you can experience guide wire perforations, which essentially can be sort of massive bleeding. So the final point, this is not in what's classed as a major adverse event, but I think it's really important, is warming of or temperature control of the patient. With adults, it's not so much a problem, but with our pediatric patients, it's very important. They cool down very quickly and as a result can arrest. So actually, by not switching on the heated cooler, or particularly when you've transported a patient somewhere, it can have seriously detrimental effects to our ECMOing. So in the essence, so I'm just briefly going to talk about transport ECMO. We could talk about this all day. Again, this isn't detailed in the ELSO didactic, but most of the incidents, in my experience, I've experienced them when you've been moving a patient, whether it be to another part of the hospital or rolling the patient to clean them. So we had an incident where we were cleaning the patient, the nurse leant on the bed, it moved the bed, and we had accidental circuit disconnection. And the important thing is be wary and be prepared. So back to the original slide. So I've discussed a range of adverse events. That is not a complete list, but they're the ones that we're expected to know as ECMO practitioners, and probably the ones we are either most feared about or can cause most damage to our patient. And therefore, these are the ones that we need to have really good awareness of. But there are many others, and the more you do ECMO, the more you'll experience them and develop your own protocols and practices to improve the safety of these. But in order to prevent this, and like I said earlier, to prevent the amount of harm we do to the patient, we need to have security layers. So I always like to use the Swiss cheese model. So the more security layers we have, the less likely we're going to have an event. And if we have good emergency protocols and we simulate these emergency protocols, it will turn a critical adverse event into not such a major problem. So our security layers, there's a whole host of them, and I'm going to go through a couple of scenarios in a moment. So they're checklists, the alarms on our ECMO circuits, our eyes and our observations are the most important. Changing in practice when we know something's not quite right, and really strong protocols. So how can we reduce the risk? So like I've mentioned, the security layers. So one thing is your circuit design. So your circuit design is your first security layer. So in my organization, we've had many incidences where we had the stopcock or the pressure monitoring on the drainage side, or P1 as it's commonly referred to, become damaged and entrained air into the circuit. So as an organization, we have removed any access on that. And as a result, our air incidents have gone from several to zero. So it's about making your circuit safe, and we have come around and we've realized there are other ways we can measure the degree of negative pressure or filling of the patient. So by designing your circuit in a really simple way and a thoughtful way can minimize the amount of risk to the patient. Any access we have on the circuit is between the head and the membrane lung or oxygenator. And that is so if there is an event or if air is entrained into the patient, that one that we fear the most, then the oxygenator can act as an air trap. And then finally, we have absolutely minimal access post-membrane. And that's because there is nothing to slow that thing getting to the patient. So the only thing we have is our pressure monitoring post-oxy, and it is a point where we would give clotting products if we need to. So again, circuit design, a good security layer. Circuit positioning, something as simple as that, is a good security layer. So we found that if we have the ECMO circuit at the bottom of the bed, people come along and fiddle and play and stuff like that. So we've moved the ECMO circuit to what we call a safe place where people are less likely to start walking past it, touching it. And again, simple things by doing that reduces the risk of an incident happening. And another one is cannula securement. So we secure the cannula to the skin. Obviously, it's sutured in. We have clear dressings and they're regularly checked. So these are all different ways we reduce the risk, for example, of inadvertent decannulation. So I'm not sure if you can see underneath that slide. So underneath that slide, it shows a protocol, a standard operating procedure. So for everything we do with our ECMO patients, there is a standard operating procedure. Now, and it details who does what, who takes the ventilator, who takes the lines, and every member of that team, for example, during the transport of a patient to the CT scanner, knows exactly what they are doing. So nothing gets missed. On top of that, there are useful checklists. So what do I mean by useful checklists? So ones that aren't too long and that are simple and are very clear. So on the front there, you have a simple checklist. And then once you've got your standard operating procedures, you've got your protocols in place of how you're going to do everything, you've got your circuit designs optimized, you practice and simulate it. And once you practice and simulate your ECMO practice, you then have to get on and doing it. And the very important thing with this is that as you do ECMO, things will happen, things will go wrong, you will have clinical incidences, you must evaluate, you have to learn, and you have to change your practices. So, final slide. So in summary, we should be prepared for all eventualities. We must have good protocols and we must have simulated these protocols. So if an event happens, we know how to deal with it. We know what our emergency protocols are, and we're not caught unexpected. And we are proficient in dealing with a critical adverse event. So, like I mentioned, we're going to have our security layers in place, our checklists, our protocols, our observations, all these things to minimize the events happening, and then be really well prepared should something happen. And that's it. Thank you.
Mrs. Price, thank you very much for giving us this impressive lecture. Thank you so much. I have visited Leicester Hospital, University Hospital 30 years ago when I was training in the UK, and I was very impressed by the hospital. And your lecture showed us how much good work you're doing there. And you showed us very clearly how many parameters we have to follow when dealing with ECMO, and how much intense attention we have to pay while using this machine, and also how many improvements there have been over the last decade with these equipments. However, I would kindly ask another specialist from Virginia, Mr. Christos Kalaritis, who can we connect with him, please? Mr. Kalaritis from Richmond, Virginia, United States. He is the director and chief of perfusion and ECMO at the Children's Hospital of Richmond Heart Center from Virginia. Mr. Kalaritis, if you can hear us, you are kindly invited to comment. Thank you very much.
Lisa, that was an excellent overview of ECMO and all the structure that you have in place. It's a model that every heart center should have. to structure an ECMO program. Now, my question also as a comment is, how much of your time as a perfusionist do you dedicate to the ECMO program? And because we always run into the challenge of individuals asking us, how much time does it take to do all this?
I think the answer is it depends on the organisation setup. So the role of the perfusionist in my organisation is we obviously set up the ECMO circuit, we build prime, put the patient on ECMO, transfer the patient back to the ICU, and then we hand over to an ECMO nurse specialist. Now, we're very lucky that we have a large number of ECMO nurse specialists. So beyond that point, it's the only thing we deal with is troubleshooting or moving the patient, and so on and so forth. The other thing that we do a lot of is 95% of our ECMO cannulations are actually done at a referring hospital, because the majority of our work is respiratory ECMO. We do obviously do both. So it's really hard to have a hard and fast rule. I think it depends on the organisation setup, what you're doing, if you're doing more VA ECMO post-cardiotomy, or you're doing respiratory, where you are cannulating. And also for us, I don't have the greatest number of perfusionists. We're supposed to have 16 perfusionists, but that's not just for ECMO. We obviously have a heavy cardiac program as well. So we're kind of tugged between, pillar and post. So I don't think there's a right way or a wrong way. There's only the way that suits your organisation. So for me, if I spoke to yourself, it's nice to hear what you do, because I can pick up tips and tricks, things that we can apply maybe to our organisation, but it's a very individual thing. But we write the protocols from that point of view. We train the ECMO nurses. We teach on the ECMO course. We teach the ECMO consultants, the medics. So the perfusion is the fundamentals are led by the perfusion department, if you like.
Right, and I think that's what the message is out of this, is that I think that perfusionists are the individuals who are the most qualified and the most competent to be the leaders in ECMO. And it's the same situation here at Virginia Commonwealth University on the pediatric and adult side. The perfusionists are the leaders. We often delegate to other individuals after the major events, but I do think that the perfusionists have to be the leaders. It's in our competency and our scope of practice to do this, and clearly this is extracorporeal circulation. So congratulations again on an excellent presentation, an excellent overview. And one last question: are you also Center of Excellence recognized as well?
So, so the answer is no, and the reason is they refuse. My hospital is very tight and refuse to pay the money but all our didactics is in line with the ELSO, but they refuse to pay for it. So unfortunately,
based on what I see and your presentation, you are definitely an ELSO Center of Excellence candidate.
Thank you very much. I mean, I like to think we do follow the didactic. Our courses meet the didactic, and I am part of Euro ELSO, so that we do make sure we do that. We've been doing a lot of ECMO. We've been doing it a very long time, but they won't pay. My hospital organisation just will not pay the money for us to go through the process, which is very sad.
Sicharitiria, congratulations.
Thank you both. Thank you both, Lisa and Christos. Thank you both for being with us. It was a great pleasure to have you here, and we enjoyed your lectures very much, both of you. And now, ladies and gentlemen, we have to carry on.